Hey everybody, hope everyone's doing well. Uh, this lesson I definitely wanted to record because it's a little tricky, especially when you start doing some of the problems. You need to have a little bit of an explanation for a couple of the aspects of the Le Chatelier's principle. So this part of the unit is all about um, when equilibrium changes. So we know already that equilibrium is when a forward reaction, the reactants to the products happens at the exact same rate as the products going backwards to the reactants. Now, a reversible reaction can go either way. Now, as we know, one reaction will happen a lot more easily than the other. Whether it's endothermic or exothermic, it's going to happen. One will happen easier than the other. Regardless of that, it can still happen both ways. So today we're going to be seeing what happens when or what causes these shifts in equilibrium and what happens when there's what we call stress being put on a system. So here's an example. So they're showing you the collision theory and how this equilibrium is going to shift because of this collision theory. So as we know, things are bouncing around in a system. So we have molecules bumping into each other with enough energy and in the correct orientation or position where they are making something new. So here's a reaction where we have SO2 and NO2 making SO3 and NO. So it's saying what would happen if you were to add a little bit more of the SO3, if you were to put more of this stuff in there. If you add more of that, you're going to have more SO3s in the system. And when you do that, it's going to cause the reaction to what we call shift in this direction. So the double arrow is going to look a little bit more like this. We're going to have some reactions going to the right, most of them are going to go to the left. And what's going to happen here is the SO3, the extra SO3, is going to be colliding with the NO. And we're going to have collisions, little bursts of energy, the activated complex making, what's going to happen? It's going to make more of those SO2 and NO3. So these numbers are going to go up. And this number, the NO over here, is going to go down. All right. So they're showing you here in this explanation, the addition of SO3 will cause more SO2 and NO2s, which are the reactants, more of them, but a decrease in NOs. Right? Because as we go down, as the NOs are being used up, what is the combination of the SO3 that we're adding extra of, the stuff that we're trying to alleviate and get rid of? It needs to bond with the NOs, the other product, and form, going backward in this left direction, forming more reactants. So as we know, in a forward reaction, we have reactants turning into products. That's how we're generally used to seeing this. But in a reversible reaction, the tables can turn. So we could have the reactants over here and the products over here. It goes in the other direction. But when we read these problems, we're just viewing it as how we read it. Reactant side on the left, product side on this side. This example, as well as many others, can be analyzed more simply by the Le Chatelier's principle. So let's see what this stands for. All right, so imagine you squeeze a balloon on one side. So if this were animated, you see that the squeezing is going to happen here. Air is going to move from one side. Air that was here that's being displaced is going to move to the other side. So the stress here, is the squeezing onto the left-hand side of the balloon. When there's pressure being applied to the balloon, the air inside is being pressurized. And and pressure is always trying to go from high pressure to low. So what's going to happen is the air is going to move over to the right to where there's less pressure, and it's going to relieve the stress. All of these examples that we're going to see is similar to this balloon squeezing, the hand squeezing the balloon analogy. Now, Le Chatelier's principle says that when a stress is applied to a system in equilibrium, the reaction will shift in a direction that relieves the stress, and a new equilibrium will be established. So we're used to seeing something like this. It's where the reactants are going through a reaction and become the products. And we also just said before that we actually can go in reverse. So this double arrow is called a reversible reaction. So C and D can turn back into A and B. These reaction goes in both directions. So the types of stresses can be changed in concentration, changes in pressure, and changes in temperature. We're going to see all of these here today. The first one here is a change in concentration. These are arguably the easier of the different stresses, easiest to imagine and the easiest to grasp. So the first thing here is we're going to see what happens when there's a shift due to an increase in concentration of reactant. So if the concentration of one of the reactants is increased, meaning for some reason we add more of one of the reactants. So let's say we add a little bit more A. So we're going to be putting more of this A in, more A is being added, and we're going to see what happens to this equilibrium. So imagine this to be like a balance, like you saw in that Edpuzzle video, it was like a seesaw. So it's kind of like a seesaw here, we have like a seesaw with a pivot point, and you have your reactants and your products. And if you were to add more of the reactants, let's say you add more reactants, what's going to happen to your seesaw? It's going to go down, and the products are going to go up. Therefore, everything's going to be pushed down. That's out of equilibrium. So what has to happen? The reactants have to turn into products. Imagine that the products now are going to be formed. More and more products are going to be formed. And what's going to happen is the product side is going to go down and balance it back out to a new equilibrium. So what happens when you add an additional reactant? The shift of the equilibrium is going to move toward the product side, meaning the forward reaction, the reaction that makes products, is going to be favored and is going to be happening a lot more. So the reaction is going to look a little bit more like this. Technically, you'll have some reactant, some of the reverse reaction happening, but you're going to have a shift towards the product side, meaning the A and B are going to collide with each other because there's a whole lot more A's in there now to bump into the B's and make more products. So the reaction will shift to make more products, the C and D, until there's that point where the two arrows are the same size again. So they're going to knock themselves out of equilibrium. More of the forward reaction will happen until you have a point where the two arrows are now back to the same size. Now let's see what happens when there's a shift or a decrease in the concentration of a product. So instead of having additional of something being added, let's see what happens when you have a subtraction of something. So let's say that D, you have less and less D, you take some out. I've seen it described as having a hole. So imagine you have a hole over here, you're taking away some of the product and there's a vacancy to fill that space. Almost like when you have your seesaw, if you have your seesaw that normally we want to be here with reactants and products, normally if you have now you take away some of the products get lighter and you're going to end up with the same situation where there's less product and the same amount of reactants. And the reactants, there's more reactants than there are products because some of the products had left, some of the products had gone away. And what do you need to do? It's going to shift to the right to fill that hole, fill that gap, and fill that vacancy. So there's going to be more of the A and B interactions. The reactants are going to turn into products in an attempt to make more D, make more of the product D to fill that space. So changes in concentration are pretty straightforward. If you're increasing, it could be a product that you're increasing too. Whatever you're increasing, the reaction is going to go in the opposite direction. So let's say you were to add, let's say that you were going to add more C. That means that you have more product than you're supposed to have. There's an imbalance here. That now, which direction would the reaction shift? You're adding too much to the products. You're going to see the reaction go to alleviate that stress. It's going to make the reverse reaction happen. More of those things on the reactant side are going to be made because there's now more C's to bump into those D's, and you're going to have a reverse reaction being favored. Now, when does it stop? It's going to happen. Most of the more reverse reactions in product, it's going to stop when there's a new equilibrium, when that balance comes back, when that seesaw is established again. As soon as everything's knocked out, as soon as you have a weird imbalance like this, you're going to be shifting everything towards the direction that is unbalanced. The next thing, temperature. Now, this is a little tricky. This can be something that's a little hard to imagine, but as we know from thermochemistry, you can include temperature, or heat, I should say. You can include heat as a reactant or product. Like when you did those thermochemical equations, you included a certain number of kilojoules in the equation as a reactant or a product. Okay, so let's say we're dealing with this reaction here. A and B are the reactants, C and D are the products. The left-hand arrow is showing you that this is an exothermic reaction going to the right, and then endo is going to be going to the left. So that would be what is shown in that double arrow. Okay, so if this is the case here, and the exothermic is the right-hand reaction, what happens in an exothermic reaction? Energy is being released. It's going out into the outside world. So let's put in a value here. All right, so now I'm going to write it out as if this were a part of this reaction. So here, this is an exothermic reaction going left to right because we have a reactant and a product that's going to be making reactant A and B, making product C and D, but releasing at the same time 87.2 joules of heat. That's an exothermic reaction going to the right from the left. Endothermic, we know, is the opposite. In endothermic, we're taking in energy and we're storing it inside. So in the reverse reaction, going to the left, 87.2 kilojoules of energy combined with D and combined with C is going to make A and B. So the endothermic version of this is the left to right version. The exothermic was the right to left. The exothermic is the left to right, where energy is being released. So we're just going to leave this picture up here. We're going to leave the 87.2 kilojoules, and we're going to see what we can, how we can understand this shift. So if the temperature increases, let's say we have more temperature, more heat. So the temperature increases, more heat is applied. So we have more heat being applied. What's going to happen to this shift? Think of heat as a product or reactant. Think of it as something that is going to knock that balance off, knock the seesaw off balance. You're adding more of something to the right side of the equation. The system wants to get rid of that imbalance, that unbalanced seesaw. Which direction will the reaction proceed to alleviate that imbalance or knocked down seesaw? We're going to have more and more reactions happening to the left to get rid of the extra heat and balance it out. It's supposed to have 87.2 kilojoules. We've added extra. It doesn't like having extra, so the system is going to bring it down until it reaches 87.2 again. It's kind of like your body. Your body's temperature likes to be 98.6. If it gets too hot, you have processes that happen to bring the temperature down. So imagine 87.2 kilojoules of energy is the amount of heat that is supposed to be released in this reaction. If you add too much heat, it's going to shift the direction to the left to get rid of some of it. All right, so let's see another example here. All right, so we have heat being added there. Now we have a shift that's due to a decrease in temperature. So that means that we're going to be having some of this heat leaving. So let's say we have some of it leaving like this. Some of the heat is leaving, and now there's less heat than there's supposed to be, 87.2. Imagine there's a hole here that we need to fill. And what's going to happen, there's a vacancy there or a hole that needs to be filled. We're going to have a reaction that's going to proceed to the right to fill that hole. So again, imagine that 87.2 is the magic number. Imagine we take some of that heat away, and it's going to be now like 50. What's going to happen? The reaction is going to happen in the exothermic direction to go from 50 back up to 87.2. So you have to treat the heat as if it were a product or reactant. All right, so one more thing. Let me just pause it and reset this for you. Okay, so let's review something here. So you don't always see the heat being written into the equation. Like you don't always see it on as like a product, like we had before, plus whatever. If you have the delta H, or the enthalpy given to you, and it's negative 56 kilojoules, what does that tell you? Is it endothermic or exothermic? Where do you write in the 56 kilojoules? Think about it. It's a loss, right? Energy is being released, I should say. So this is a negative, this is a loss. So when you lose energy, when energy is being released, what is that, exo or endo? Energy is going to the outside, it's exo. So this is exothermic. So where would you write 56 kilojoules? Would it be written on the product side or the reactant side? You would write it on the product side. Sorry, because it's being lost, 56 kilojoules, all right? In the example down here, you have an enthalpy that is positive, meaning energy is being taken in. We're gaining energy. where would you write the 41 kilojoules? All right, this is an endothermic reaction, so this would be written on the reactant side. So let's just say 41.0 kilojoules. Wherever you recognize the energy to be based on if you have like this -8, if you have this delta H and whatever the enthalpy is, just I would recommend to write it into the equation, making it a thermochemical equation, and go from there. Because if it says that you're gaining temperature, you're gaining heat, then you're going to want to write it wherever you're going to add your heat to wherever you have your heat in the equation. So let's say you're adding heat over here, you're going to say, okay, well, I'm adding product, it's going to shift to the left. Or let's say, okay, I'm adding reactant because my heat is over in the reactant side because it's endothermic. I'm adding heat over here. That means that there's too much heat, it's going to shift this way. So in order to know where the heat is, write it out. Then you can follow the situation and say, okay, I'm losing heat or I'm gaining heat. You can draw your arrows, you can however you want to think of it, and see that the shift is going to go in the opposite direction. Okay, so the last one here is pressure. Now, for pressure, this only applies to gases. So whenever there's a question about pressure, take a look at the equation. The equation's always going to have gas, 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 gas. All of them are going to be gases. So if you think about it, we're going to have two gases combining, making two new gases. So this is only going to be occurring in containers where you can pressurize the container and you have gas reactions happening. Here we have a situation where substance A is reacting with substance B to make substance C. So let's say we have substance A reacting with substance B to make C and D. Okay, now, what do you think these lower cases are? The lowercase italicized ones, what do they represent? If the capital letters are the substances themselves, what do we always write in front of something to tell us how many there are? Anybody remember? We call those lower letters in front. These represent the coefficients. So those little letters, A, B, C, and D, in front of the capital A, B, C, and D, represent the amount of molecules, or amount of moles, I should say, of A, or the amount of B, the amount of C, the amount of D. So you have to recognize what those letters mean. Now, let's just say that we have an increase in pressure. All right, so the pressure is going to increase in the whole container. The reaction is going to shift in one way or the other. Now, the rule here is because there's nowhere to go, it's in a closed container, and the pressure is increasing. Imagine a room that's extra crowded, and you make the room smaller. It's going to try to alleviate the pressure because you can't spread the molecules out anymore because in fact the room's getting smaller, the pressure is increasing. What's going to happen here is the system is going to favor the side of the reaction that occurs to make the least amount of molecules. This is a little difficult to imagine. Let's just give you an example. Let's say that A has 2, so let's say this would be 2, and this would be 2. Let's say this is 3 and this is 4. All right, so those are the coefficients that would go in front of those. If you were to add up the amount of molecules on the reactant side, how many molecules total are there? 2 plus 2, we have 4 moles of the gas on this side. How many on this side? 3 plus 4 is 7 moles. All right, so imagine we have pressure is increasing, it's getting tighter and tighter and tighter. The system is going to favor the direction that makes the least amount of moles. All right, so if you were to go in the direction of the right, is that good? Is that what the system wants? Does it want to go from having 4 moles of something to making extra of something, 7 moles of the product? No, it doesn't want to do that. It wants to actually go in the other direction. So what's favored here is the situation where 7 moles of something turn into 4 moles of product, because now there's more room, because if there's less molecules bumping around, then it's going to be less crowded. So when the pressure increases inside of a closed container, so let's say this is inside of a closed container that is getting smaller, pressure is increasing, and let's say that this container is now smaller. The molecules in here, the little molecules in here, are going to be more crowded. So in this situation, the better situation is, the better solution here is to take make the reaction happen that is going to reduce the amount of moles. That's when the pressure increases. Let's say we have the opposite situation. The pressure is going to decrease, so like the container gets bigger. And there's more room for the reaction to take place. The room got bigger. In the same situation here, we have 4 plus 2 is 4, so we have 4 moles of reactant on this side, and we have 3 plus 4 is 7 on this side. So when the room gets bigger, when there's more space, we're going to be seeing a shift going in this direction. All right, so it's different from the example up here. So if we were to take all these away, so they're saying here, if you have the amount of, it's a little bit confusing the way they wrote it here, but if A and B add up to a greater number than C and D, let's say this was 7 and this was 4, these two, A and B, these two are going to add up to 7, and these are going to add up to 4, you're going to see a shift going in this direction. So it's just the opposite the way I did it. All right, so the big takeaway here is what you do whenever you're doing a problem like this is just add up the coefficients. Who cares what, we don't even care what these things are. It literally doesn't matter to us at all. We don't care what the substances are. We're only focusing on the coefficients. That's literally all we care about for a question like this. As long as they're all gases here, which they're probably going to be, you just count the moles. So I'll give you an example, and you can kind of predict it. So looking at the example here, where we have hydrogen gas and nitrogen gas becoming ammonia, all you do is count the molecules, count the moles and the coefficients. So if we add these up on the reactant side, we have 4 moles, because we have 3 plus 1, and then on the product side we have 2. So let's say that we increase the pressure. So if we increase the pressure, then which way would the system be favored? Which direction would the equilibrium shift, like we say? Increasing the pressure, no more room, gets a whole lot more crowded, so it's going to favor the forward reaction. If the pressure were to go down, there's more room to move around now, it's okay. It's okay to have more molecules, everything would shift in the other direction. Okay, this would be a decrease in pressure. Okay, so if that didn't help you, you could just search YouTube. There's a bunch of really good ways of explaining this, but I don't want to go any more with this. The explanation should be enough for you to do the assignment associated with this. All right, good night and stay well.